Thank you. This is joint work with Ehsan Emamjomeh-Zadeh and David Kempe. So let's talk about stable matchings. So in 1962, in their seminal paper, Gale and Shapley asked the following question: given a set of women and a set of men where each man strictly ranks all the women and each woman strictly ranks all the men, can we find a stable matching? That is, can we pair up all the participants into man-woman pairs such that there's no man and woman who are not matched to each other, but prefer each other to their assigned partners? They gave a resounding yes answer, saying that for every set of men and women and for every preference structure whatsoever, a stable matching always exists. And the proof is via a beautiful constructive algorithm, and notably requires full access to the participants of the preferences. So this was on the econ side. About a decade later, on the CS side, Don Knuth, in his famous 4 lectures turned book on algorithms via the lens of stable matching, noted that starting with some stable matching and iteratively resolving one blocking pair at a time, so we're iteratively finding a man and a woman who are not matched with each other and matching them together, and we're iterating over that. And that may actually cycle, so it may actually not reach a stable matching. That's the naive algorithm, if you wish. About 2 decades later, again on the econ side, we have a positive result by Roth and van der Watte, saying that if the blocking pair in Knuth's algorithm is chosen uniformly at random among all blocking pairs, then a stable matching is actually reached with probability 1. And Kojima and Unver later showed this even for many-to-many matchings. And then we have, once again, a negative result on the CS side, saying that while it does converge with probability 1 to a stable matching, this may actually take a number of steps that's exponential in the size of the market. And this negative result is our point of departure for today. And we're going to try to use CS tools today to give a positive rather than negative result, and also hope for it to have an economic message as well. So we're going to ask, is there a smarter interactive learning algorithm with better query complexity? What do I mean by this? This algorithm must still work in the same model. The algorithm proposes a matching. If it's stable, done, the algorithm wins. If it's not stable, then some blocking pair is revealed, say even adversarially, and fed back to the algorithm. The algorithm now can propose a new matching. If it's stable, it wins. If it's unstable, another blocking pair is revealed. The algorithm then, based on these 2 blocking pairs, can propose another matching, etc. So this fits quite nicely into the equivalence query model of Anglo in 1988, also generalized by my co-authors on this paper a few years ago for learning a binary classifier. So the learner proposes generally a structure. In our paper, it's a matching. The response is either that the proposal is correct, in our case, it's a stable matching, or is being told one local mistake, which we model as a blocking pair. And previous results restated to this model basically say that the myopic learning algorithm takes exponentially long to converge to a stable matching with randomly drawn legal responses, legal meaning that they're actually blocking pairs, and may actually never converge with adversarial legal responses. And we ask, can a more sophisticated interactive learning algorithm perform much better than that? So the reason I like this question is a kind of a win-win question. If there's a negative answer to this question, then thinking back on Kamal Jain's quote, if your laptop cannot find a certain solution concept, neither can the market, and thinking about a blocking pair as somehow the naturally observed first sign of a matching unraveling, then a negative answer would cast doubt on the belief that decentralized markets, or even centralized if the designer only has access to coarse queries of trial and error, could reach a stable matching. If, on the other hand, we get a positive answer, then thinking of a blocking pair as somehow minimal informative evidence of the instability of the given matching, indeed we call this a coarse query model, then in that light, a positive answer would somehow mitigate to some extent Ackerman's negative message, showing that stability can in fact be achieved even if the designer looks only at the market through a far coarser and less informative lens than ever considered before. So preliminary attempts, first naive attempt, try all matchings, obviously exponential, not very interesting. So let's try something different. Let's fix speculative preferences for all of the participants, consistent with all the information gathered so far. We'll get to this consistency condition now. Later, for now, you can just think about, in the first steps, fix arbitrary preferences for each participant, and find a stable matching with respect to these speculative preferences and propose it. And then if it's not stable, we get back a blocking pair, W and M, that indicates that W prefers M to her match and M prefers W to his match. And one of these must contradict the speculative preferences because the matching that we proposed was stable with respect to the speculative preferences. So if we keep such a table for each participant, so this is for the woman W, we keep this kind of table to help us keep track of whether she prefers any man to any other man and vice versa, we get a bit into this table, for example, telling us that W prefers M2 to M3. Now we repeat what I mean by that. We fix new speculative preferences that are consistent with what we have so far with all of these tables. We find a stable matching with respect to them. We propose. If it's stable, great. If not, we get another blocking pair. Maybe it goes into tables of other participants. Eventually, we'll get some more bits for this woman. Maybe we'll get that she prefers M4 to M1, and then after a few steps, we'll get that she prefers M3 to M5. And eventually, after n to the third order queries, meaning n over 2 queries for each participant, all preferences will have been revealed. So when we propose a matching, it's for sure stable. So can we do better than n to the third? What we did here, we essentially, unless we were interrupted by winning, by finding a stable matching, we actually essentially sorted each participant's preferences. And I say sorted because we got information about pairwise comparisons. And while it's appealing that we got into the third polynomial query complexity, it's quite satisfying that we actually encapsulated a quadratic sort. We needed n to the square n squared queries for each participant. And in CS, we really, really like to sort in n log n queries rather than n squared. Problem is that canonical sorting algorithms can choose the next comparison, while in our model, we cannot target a specific comparison. We propose a matching, and we're adversarially given one comparison that conflicts with it. So the question is, can we nonetheless spend at most n log n queries per participant to interactively learn a stable matching with overall n squared log n queries? And our first main result is going to be that we can actually do that. And here's the high-level view of the algorithm. So the idea is essentially the same algorithm, but choose the speculative preferences in a smarter way. Choose them such that any conflicting comparison indicated by a blocking pair for any participant reduces the number of preferences for that participant by at least a constant fraction. So since each participant has n factorial possible preferences to begin with, we end up having to spend log of that many queries, so n log n many queries on each participant for a total of n squared log n queries, and that's great. But how do we choose such speculative preferences in this smart way? How do we know that even exists? So here our main tool is proportional transitivity, so let's talk about that. So let P be any partial order whatsoever. Standard transitivity tells us that if M precedes M prime in all linear extensions of P, and M prime precedes M double prime in all linear extensions of P, then M precedes M double prime in all linear extensions of P. That's trivial. What about if M precedes M prime in 80% of linear extensions of P, and M prime precedes M double prime in 80% of linear extensions of P? What percentage of the linear extensions of P have M preceding M double prime? So thinking about 80 and 80, let's have them overlap the least. You maybe would say 60%. The miraculous thing here is that actually 80% holds as well, and that's use very beautiful proportional transitivity theorem that says that you can actually replace these three 80s consistently with any percentage higher than 80. You can have 90, 90, 90. You can have 100, 100, 100, but that's of course less interesting because that's normal transitivity. So let's use that to construct our n squared log n algorithm. So we're going to choose the speculative preferences for a single participant, fix a participant, and do the following. Let P be a partial order of all data gathered so far. So data gathered so far is pairwise comparisons. So there's a partial order underneath that. And the possible preferences are actually precisely the possible linear extensions of P. So let P prime be the partial order where M precedes M prime for any M and M prime, if and only if in at least 80% of the linear extensions of P, we have M preceding M prime. So by proportional transitivity, this is a cyclic, this is an order. Why? Because if M precedes M prime and M prime precedes some M double prime, proportional transitivity tells us that M double prime cannot be necessary for M double prime to precede M. And also P prime is an extension of P, because whatever holds in P holds in 100% of the linear extensions of P. So all extensions of P prime are actually possible preferences, and we just pick some linear extension of P prime as the speculative preferences. And the crux of the analysis is that any conflicting comparison indicated by a blocking pair is actually consistent with less than 80% of linear extensions. If it were consistent with more than 80%, it would have been in P prime, and hence with the extension of P prime. So it eliminates at least 20% of the possible preferences. So we get n square log n queries. Great. Can we efficiently find P prime? The problem is that for M and M prime to tell whether M precedes M prime in at least 80% of linear extensions on P is not easy. Luckily, there's an algorithm by Huber that lets us efficiently sample uniformly at random, that's the important part, linear extensions of any given partial order. So we can sample many extensions of P and sample them and say that we put M preceding M prime and P prime if in the linear extensions that we sampled, at least in 85% of them, M precedes M prime. And it's unlikely that we'll make a large mistake here. So by proportional transitivity, P prime is still a cyclic with high probability, because thinking that it's more than 85% and eventually having it less than 80% is quite unlikely. And for the same reason, it's consistent. Any conflicting comparison is consistent with less than 90% of linear extensions of P with high probability, so it eliminates at least 10%. So we're back in business, and yes, we can make this efficient. So what about a lower bound? So there is a paper by how do you pronounce it? Never mind. They show a robust n squared lower bound on the query complexity, on the communication complexity of finding a stable matching, but in a starkly different model. They have arbitrary bitwise queries, but these must involve each of them only a single side of the market, only the preferences on a single side of the market. And to drive that point home, note that the lower bound of n squared there also holds for verifying stability, while in our course queries, you need only one query to verify stability. Gale and Shapley's algorithm actually falls squarely within their queries, so it requires n squared log n bitwise queries, so it gives an upper bound of n squared log n. That's actually the best known upper bound, so there's a gap here. And queries in that model, even though they're incomparable to ours, in our model you have one kind of query that's answered adversarially. It's not a bitwise query. They have bitwise queries, but can only arbitrary, but can only target one side of the market. Nonetheless, their queries are stronger in the following sense. N squared of their queries can simulate one of our course queries. No number of our course queries can simulate one of their queries. So a polynomial algorithm in our model applies a polynomial algorithm in theirs. A lower bound in theirs implies some lower bound in ours. Specifically, their n squared lower bound implies a trivial omega of 1 lower bound in ours, but we nonetheless give another n squared lower bound in our model. Holds even an expectation, even if the prefs are known for one side of the market and IID for the other side. It's a less elaborate proof than the above paper, as you may expect, because course queries, lower bounds are easier, upper bounds are harder, generally speaking. And what's curious here, it's the same gap of n squared versus n squared log n as in that widely different model. We don't have a very good technical explanation, but it seems that the crux of both of these questions is, can you really find a stable matching without completely nailing down the preferences? So let's move to talking about many-to-many matchings. Firms and workers, Roth 84, 85, many extensions. Each firm can be matched to many workers. Each worker can be employed by many firms. The canonical thing here is responsive preferences. Each firm has an order over individual workers plus a quota of the number of workers that can employ. Each worker has an order over individual firms plus a quota. And a course query will look exactly the same. Propose the matching in response, either get stable or get a blocking pair. Notably, a blocking pair here reveals that F prefers W to some worker currently assigned to F. It does not reveal to whom. So if we have 6 workers assigned to F, then we only are told that W is preferred to one of them. We're not told to whom. If we were told to whom, we would have gotten a bitwise query. We could have run the one-to-one algorithm. This is even coarser information, does not imply any single pairwise comparison in any preferences. This is very much in line with our motivation of working in the weakest, coarsest model, revealing, quote unquote, minimal informative evidence of underlying preferences. And the question here is, again, can exponentially many queries be avoided? It's tricky. there's actually a slight variant of this problem, looks very similar, that we show to be NP-hard. And I should know that all challenges here are already in the popular one-to-many matching. We're only doing many-to-many to be more general. So there are a few challenges in adapting our algorithm to the many-to-many setting. The first one, given gathered information, find some speculative preferences. In the one-to-one settings, gathered information was pairwise comparison, it was a partial order. We know that we can extend a partial order into a linear order using topological sort. What if your constraint, the gathered information so far looks like this? M1 is greater than one of these, M1 is preferred to one of these as well, M5 is preferred to one of these, etc. What do? Turns out you can still run a variant of topological sort that we introduce. If you think about it, there must be at least one man that does not appear on the left-hand side of any of these constraints, because appearing on the left-hand side means that you're preferred to someone, and there is a man who's not preferred to anyone. Choose such a man that doesn't appear on the left-hand side of any constraint as the last person on the speculative preferences, and repeat. That's efficient. We can find an order that's consistent with all these preferences. If we just do this, then we may have to accumulate the entire set of possible preferences for each participant. So we're going to have n to the q possible preferences for each participant. So n to the order of q overall queries, also runtime. It's appealing because it's polynomial in n. It's quite dissatisfying because it's exponential in q. So the next question is, can we drop the exponential dependence on Q? Much like earlier, can we find good speculative preferences? Ideally, we would have wanted speculative preferences such that every conflict rules out a constant factor of the possible preferences like we had before. This is too good to hope for. You can check that even the first conflict rules out only 1 over Q plus 1 of the preferences. That's less than a constant fraction. So ideally, we would shoot to 1 over Q. We don't know how to prove that. What we know how to prove is to find good preferences in the sense that a conflict rules out at least 1 over n of the possible preferences. If you take the log, you get n to the 3, n to the third log n queries. That's still polynomial and independently of Q. It's a bit weird to say independently of Q when Q is bounded by n. What we really would have wanted is n squared Q log n. But we don't know how to show that. That would have been in line with ruling out 1 over Q any moment. So that's an open question. Finally, given gathered information, how do we efficiently find good speculative preferences? Similarly, but dissimilarly to what we had before, a way to implement finding good speculative preferences in an efficient manner would have involved uniformly sampling an order that's consistent with all the constraints so far. We don't know how to do that, so we leave this question open. In particular, can you do such sampling? In particular, this relates to an open question regarding mixing times of some stochastic processes, notably generalizations of the Karzanov-Kachyan chain. And there, if you have a quota of greater than 1 in our model, it corresponds to what seems like non-convex constraints on that chain. So it's very unclear on how to show rapid mixing of that chain. Oh, so to sum up, despite very coarse, you could say minimal info queries and adversarial responses, we can find a stable matching using polynomially many queries. There is a big gap between n square log n upper bound and the n square lower bound, curiously very reminiscent of gap from other studied widely different models. A fairly small difference of n to the third versus n squared log n in the one-to-one case became a dramatic gap of exponential versus polynomial in the many-to-many case. So there is a lesson to be learned here about chiseling as hard as you can, even removing that n over log n in the one-to-one case, because it actually became very useful when we generalized. And as I said, the open question, can you do many-to-many matching of this model in a way that's computationally efficient? So that's it. Questions? And can anyone write in the chat what this picture represents? So that's actually a stable marriage. So thank you so much for